SwayamPrabha. Digital India. Educated India.
Now let's go back and look at the two polynomials that we looked at, and let's apply these conditions to the two polynomials, right? So what was d1 of s? It was s cube plus 2s squared plus 3s plus 1, correct? I hope everyone agrees, right? So now how do I construct the Routh's array? I write s cube, s squared, s power 1, s power 0. Right, so that's what I do. Then I take the first two rows, right? Then I start filling the coefficients, right? What are the coefficients? 1, 2, 3, 1, right? That's it. I have exhausted my coefficients. Okay. Now if I want to go to the s power 1 row, what do? I multiply 2 with 3, I get 6. I multiply 1 and 1, I get 1. So 6 minus 1 is going to be 5, and I divide 5 by 2. So I get 5 by 2. Okay. So would I have any other entry in the s power 1 row? No, because there is nothing to the right of the column 3 and 1. That's it, I stop here. Okay. Now I go to the s power 0 row. Okay. So now then I consider the s square and s power 1 row, right, for the s power 0 row. So what do? I do the same process. 5 by 2 times 1 minus 2 times, when you do not have an entry, you take it as 0. Okay, that is once, not the first entry, but then the other entries, right? When you have reached s power 1 row, you don't have an entry here, right? So you take it as a null entry. So 5 by 2 times 1 minus 2 times 0 is 5 by 2, and then 5 by 2 you divide by 5 by 2 itself. What will you get? You will get 1. So now let's look at the first column of the Routh's array, right? What can we observe? No sign changes, right? Because one can observe that all entries are positive, right? So this implies that all three roots of d1 of s have negative real parts. So I hope it's clear, right, how we applied it here, right? So please note, I'm not calculating the exact roots per se, right? Did I ask you to solve the polynomial for the roots? No, right? That's what I'm reiterating here, right? At this stage, we are only interested in figuring out the location of the roots, okay? So we did not solve for the roots, right? So we are only concluding that all three roots are in the left of complex plane, where we need to solve the equation, right, to get the exact values of the roots, okay? So that's the first polynomial. So now let's go to the second polynomial. So what happened in d2 of s? We wrote it as s cube plus 2s squared plus plus s, I can call it as s, right, plus 3, right? We just swap the s power 1 and constant term coefficients, right? So let's do the Routh's array construction once again. S cube, s squared, s power 1, s power 0, right? So we have, once again, we fill in the first two rows, 1, 2, 1 and 3, right? Now we want to calculate for the s power 1 row. What do? We multiply 2 with 1, subtract 1 and 3. What are we going to get? Minus 1. Right, minus 1, I divide by 2, I will get minus 1 by 2, okay, and that's it, right? I have exhausted my coefficients. So we come to the s power 0 row. For the s power 0 row, we consider these two rows, right? So minus 1 by 2 times 3 is going to be minus 3 by 2. Minus 3 by 2 minus of 2 times null entry is going to be just minus 3 by 2, and minus 3 by 2 divided by minus 1 by 2 is going to be 3 plus 3. Okay, so we immediately look at the first column of the Routh array. What can we see? There are two sign changes. How come there are two sign changes? You see that from 2 to minus 1 by 2 is one sign change. From minus 1 by 2 to 3 is another sign change. Okay, so that's how we get two sign changes here. Okay, so this implies that there are two sign changes in the first column of the Routh array. So this implies that, what does it imply? So this implies that there are two roots in RHP, and obviously where should the third root be? In LHP, right? So plus one root in LHP. Okay? Yes, please. No, why not? Because yes, that's a good point. Okay, how come, like in this example we are sure that it's not in on the j omega axis? Okay, so let's argue from two perspectives. Okay, so that's a good question. Okay, let me repeat his question. Okay, so if you logically apply whatever we have learned till now, the only conclusion we can draw based on the facts that we have written under the Routh's criteria is that there are two sign changes, so two roots should be in the right of plane. So this is a third order polynomial, right? So totally there are going to be three roots. So two roots are in the right of complex plane, so we are left with only one root. Okay, where does the one remaining root lie? Obviously, there are two ways to eliminate the j omega axis. First is by looking at the Routh array, you see that there are no zero entries. Okay, so as I told you, tomorrow we will look at special cases. That rules out the j omega axis. Second thing, you can look at the polynomial itself. See, this is a third order polynomial, right? You have one remaining root. So if I want the one remaining root to be on the j omega axis, right, I can have two possibilities. Either it should be at the origin, or it should be a complex conjugate pole on the complex conjugate pair on the j omega axis, right? Complex conjugate pair is ruled out. Why? Because I have only one remaining root. Complex conjugate pair means I need two remaining roots, right? That's gone. And so the only possibility which is left is at the origin. If you have a root of a polynomial at the origin, the constant term is 0. Is the constant term 0 here? No, right? So that's the second line of argument. So we are ruling out j omega axis.
Because we got two roots here. We got one root here, then we may have.
You may have, but once again, that's a good point. Let's say we have an example, there is only one sign change, right? Let's say a third order polynomial, we have only one sign change. Question is, I am left with two remaining roots. I can still have, let's say, a complex conjugate pair on the j omega axis. Possible, but still in that example, if you, in your first column of the Routh array, if you do not have a 0, that you rule out that possibility. Okay, as I told you, we are going to do that tomorrow, right? So yeah, okay, I think that's a good question. Okay, I hope you didn't follow that result, right? Yeah, okay. So let me write down the general Routh stability criteria, then we will go back to our example that we are doing it last class and complete it. Okay, so let me write down the Routh's stability criteria. Okay, so you see that whatever we have been discussing till now applies to any polynomial, right? You can encounter polynomials in any application. Now we are going to apply it to control theory. Okay, so I hope you can see how mathematics is applied to our subject of discussion, right, which is control design, right? So we will now see how we are going to apply it to our thing. Okay, so consider a system, it can be open loop or closed loop, right, whose transfer function is of the form n of s divided by d of s. Okay, let's say we assign whatever symbol we want. Okay, so consider a system whose transfer function is n of s or d of s. It can be just the plant, it can be the open loop transfer function, it can be also the closed loop transfer function. Okay, so any system, okay. But for control design, for us, by and large, we will consider the closed loop transfer function, okay, because that's what makes sense for us, right. So in general, consider a system whose transfer function is n of s divided by d of s. This system would be bibostable okay, that means some people will call it as asymptotically stable. Okay, if and only if, okay, if and IFF means if and only if, right. So, so that indicates necessity and sufficiency, okay, if and only if A, all the coefficients of D of s are non-zero and of the same sign, and B, the first column of the Routh's array constructed using the coefficients of D of s, okay, oh, I should say first column, right, I am sorry, I missed the word first here. The first column of the Routh's array constructed using the coefficient of D of s has all entries being non-zero and of the same sign. Okay, those are the two conditions. Okay. So once again, please note that bibostability or bibostability means like you can't have poles on the imaginary axis also, right? That's ruled out. So I can say I will have a 0 in the first column. No, I should have non-zero entries in the first column and they should all be of the same sign. Okay. So those are the two conditions as far as the Routh stability criteria is concerned. Okay, this is what is called as Routh stability criteria. Okay, fine. So we will go back and now apply this Routh stability criteria to the problem that we are doing. Okay, so to complete this. Okay, so I will just take a couple of minutes to do that. Right. So is this clear to everybody? Okay. So let me scroll down. Okay, I am just going to this problem. I will edit this files appropriately, but we are doing this problem, right, where we are looking at the PI controller, and we figured out that the closed loop characteristic equation is s cube plus kp plus 1s plus ki equals 0, right. So now the roots of this polynomial will be the closed loop poles. So do you think the PI controller will stabilize this closed loop system? No, why not? I don't even need to go any further, right? Why not? The necessary condition is not satisfied, right? So we can immediately see that. So this shows that the coefficient of s squared is 0, right? So this implies that there are no values of Kp and Ki can stabilize the closed loop system. Okay, that is the implication of this result. Okay, correct. So the PI controller will not work. So now you see why we digressed and learned the Routh stability criteria and came here, right? So you can see that our analysis becomes more simple, right? So now as the next step, let's try the PD controller, okay, because for this system, let's go ahead and try the PD controller, okay. So PD controller means its transfer function is Kp plus Kds. So we follow the same framework, okay. So let's say then G of s which is C of s times P of s. Please remember, what was the plant transfer function here? The plant transfer function was 1 by s squared plus 1, okay, that is the plant we started off with, right. So, that is going to be equal to KdS plus Kp divided by s squared plus 1, right. So, this implies the closed loop transfer function is going to be equal to g of s divided by 1 plus g of s h of s, that is going to be equal to KdS plus Kp divided by s squared plus 1, the whole thing divided by 1 plus KdS plus Kp divided by s squared plus 1, okay, and that is going to be equal to KdS plus Kp, the whole thing divided by s squared plus KdS plus Kp plus 1. Okay, so that is what we have. So, this implies that the closed loop characteristic equation is going to be equal to s squared plus KdS plus Kp plus 1. Okay, so immediately we see that this is a polynomial of order 2, right. The closed loop system with a derivative PD controller is still a second order system, okay. With this, like immediately we see that, as I discussed, for polynomials still order 2, the necessary and sufficient condition is all coefficients must be non-zero and of the same sign, okay. So, this implies that the closed loop system would be stable, would be Bibo stable if and only if all the coefficients must be non-zero on the same sign, right. S squared term, the coefficient is plus 1. So, already one coefficient is positive. So, we must have Kd should be greater than 0, Kp plus 1 should be greater than 0. So, this implies that Kd greater than 0 and Kp greater than minus 1 is the, is the feasible region, okay, for stability, okay. So, if I want to plot this in the controller parameter space, I will just stop with this plot, like so. We have Kp on the horizontal axis, let us say Kd on the in the vertical axis, right. So, how will I plot Kd greater than 0? Kd greater than 0 is this half plane, right, isn't it, right. How do I plot Kp greater than minus 1? First I draw Kp equals minus 1 and any region to the right of it is going to be Kp greater than minus 1, right. So, consequently the feasible region is going to be the intersection of the two regions, right, correct. This is the feasible region, right. This is what I called as the controller parameter space, right. If I say calculate the feasible region in the controller parameter space, this is what you need to do, okay, for the controller, fine. So, as a very simple exercise for you to do, consider the general second order polynomial a naught s squared plus a1s plus a2, apply the Routh's array to that, okay, and convince yourself that the necessary condition is also sufficient, okay. You will see that the first column will have a1, a2, sorry, a naught, a1 and a2, okay. So, what was necessary will also become sufficient for polynomials still order 2, okay. So, that is the what to say criteria for the for orders polynomials still order 2, okay. So, is it clear?